Okay. I'm going to talk about profiling and debugging tools in Legion. I will start with Legion Prof. So Legion Prof is a profiling tool for both Legion and Region applications. And it tracks timing information about tasks, copies, and instances. For example, it tracks when a task started and when it finished. And also it tracks when a region instance was created and when it's destroyed. And also it tracks how long a lower-level copy from one memory to the other has executed. And also it tracks the dependency among task copies and instances. For example, it tracks which runtime tasks were initiated by which task. Like the launching part of the runtime task will be part of the actual application task. So we need to track the dependency between the two. And also, we track which region instances were created by which task on which memory. And also, we track which copies were initiated by which task. And Legion Prof is a code blob inside the Legion runtime, which will be enabled by passing the shell :prof option. And when you pass this option, it will dump out the Legion Prof trace, which will be consumed by the other tools like Legion Prof Visualizer. So we have Legion Prof Visualizer, which takes the Legion Prof trace. And we used to build this tool using static SVG file. SVG is a vector graphics format to visualize things on the browser. And that's supported by all major web browsers. But once you have a timeline from your real application with a real setting, that it often becomes too long to fit into the one browser screen. And even if you put all those timeline information to the one SVG file, it often takes too long to visualize. And it's very difficult to navigate through the timeline to find the point that I need to look at. So we developed a new web-based visualizer, which is based on a JavaScript program that takes the Legion Prof trace and generate timeline as an SVG dynamically. And when you generate this visualizer, it will work as a standalone visualizer. So you just open up the legion_prof.html, then it will give you the interface. With this new interface, you can zoom in out for a particular time span. And also, it will render the things that you can see from a particular zoom level so that it will give you a smoother experience of navigating the timeline. And also, it supports a search of a particular task or copies or region instances in the timeline, which will give you much clearer focus on particular tasks and copies. Since this visualizer provides an interactive interface, so instead of giving you some screenshots of the interface, I'm going to give you a live demo here. Okay. So this is a timeline trace from Minio on 2 nodes. And as you can see that this timeline is for the entire application execution. So this is the beginning of the execution, and this is the end of the execution. And you can see that you know where you are located on particular timeline here. So this is this is a 10-second from the execution. And if you want to zoom in, then there are multiple ways to zoom in. You can just click some keyboard shortcut to zoom in and out. And also, you can select a particular time span, like here. Then it will give you how long the span is. And it will shows up like this. And you can always squeeze back to get the entire timeline. And you also zoom in on the y-axis to get more information from the other node. And it also has a information about the instances here, and these are skewed, but yeah. This is a timing information for the copies. And the other nice thing about this is that you can search for a particular type of task, like compute phase flux. And this will highlight the task that matches the regular expression. And you can always toggle back. And you can even navigate between different searches like this. So you can see how the time step is progressing here from compute phase block to compute limiter. And this is not just working for a small amount of data. It also works for a large. I wanted to make it scale up to tens of hundreds of nodes. So this is the timeline from the 8-node run of Minero. So this will look similar, but if you zoom out for y-axis, it will give you the entire timeline for all the nodes. And this will still very fast to navigate here. And if you can even zoom in and zoom out very quickly, like this. And so this will give you much better experience of using Legion Prof. And if you are interested in getting the entire list of shortcuts, you can get the list by hitting question mark. So this is a list of features of this interactive interface. Okay. And we have other types of support from the tool side. The first one is operation graphs. This type of graph shows the data dependencies between tasks, and it will be generated for every non-lib task. So for example, this is again from the Minero, and this will show you that there are 4 SPMD tasks here, and if you want to take a look at one of them, then you will get the operation graph for that particular instance. And for each of these tasks, it will show which logical regions are used and which physical instances are created for that task. And these edges mean that there is a data dependency between these two. So it will give you kind of high-level structure, dependency structure of the application.
So I can't quite read the small font. What type of information is printed in the blue boxes?
Come again?
What type of information is displayed in the blue boxes? You can't read it from here, at least I can't.
Sorry.
You don't have to say the details, just the type of information.
So the type of information is mostly the privilege and which physical instances are used for a particular task instance. And for different type of operation, like fence, for example, it will give you which tasks should be launched after this fence, for example.
Are you doing that per node or per GPU, or is that actually the global task graph?
So right now, this operation graph works for the entire node. So you have to collect all the log files from the node and give them to the tool that generates this graph.
But then wouldn't that list contain like all the regions in your thing? So like
right, but
running on 100,000 cores gives you a list of 100,000 IDs? Right,
that is true. But in this particular case, we only have one SPMD task for one processor. And for each SPMD task, we generate a separate graph, which will be much smaller. than having all the graphs into one single
Okay,
graph.
so that's what I was trying to get at. So you are typically in practice using these only on a per node level. So really only for the shared memory part of the system, not MPI.
So,
Just asking just because it is a hard problem.
Yeah, I'll definitely say it's a hard problem. You can leverage, what Lanchan is saying is you can leverage the task graph, the hierarchical nature of tasks, and you can display graphs for, just the parent task and all of its subtasks it launches. And, you might see a big fan out in that top level task, but then, the subtask that you see on each individual node, or like subsets of nodes, becomes much more tractable to deal with. So you leverage the hierarchy of the task, of the program task graph, or task tree to actually just visualize the parts you're actually interested in.
Yes. What do you do if some of your subtasks have dependencies between parent tasks? Like those might not be fully hierarchical.
That's the other part of the graph there.
Sorry.
So-
We can talk about that.
Okay. Maybe we should. It's worth, one of the things we're pointing out is this tool that Wanshan, so there are two sort of tools that Wanshan did Legion Prof first, and the second tool is called Legion Spy. We've done a lot more work with Legion Prof because many more users are actually playing around with that one. And people are actually using it to do profiling, debugging. Legion Spy is sort of becoming more used, but it hasn't been used as heavily by external users yet. So, doing sort of a more dynamic thing where you can actually like zoom in and out of nodes inside of this graph would be, particularly nice. And we just haven't gotten around to it because there hasn't been the demand for it. But if you guys would like to see, a more interactive aspect to Legion Spy, we'd be interested in hearing about that.
right. So this operation graph will be generated from a structured program, which means that you somehow have the structure of the inside the graph, even if you have multiple instances for the same type of task. So the plan for operation graph is that I take this graph and kind of find a repetitive structure inside the graph so that I can make it more compact and visualize for multiple nodes within a single graph. Again, when you compare this operation graph with the other type of graph we generate, this graph will embed all the child tasks into a single graph file, which means that if you have hundreds of thousands of tasks in your application run, it will not render properly with your PDF viewer. So usually what we do with this type of graphs, we reduce the size of problem, and we also reduce the size of number of time steps to get small enough, but covers all the important part of the application, and generate the event graph and take a look at it to find any semantics issues or dependency issues. Okay, so here's another type of graph, which is an event graph, which is more comprehensive, and it will show you all event dependencies between operations. So data dependencies will imply event dependencies all the time, but it's not the other way around. So sometimes you might miss some important event dependencies between operations with the operation graphs. So that's why we have this event graph. So in this event graph, you will see which tasks are launched by index-based launch and which tasks are launched by single task launch. So here you can see that index-based launch task has a different color with the single task launches. And also we track the copies between the tasks inserted by the runtime. So these copies are not the programmer's duty, but somehow runtime found that we need a data movement between these two tasks. This kind of stuff is not visible to the application program itself, so you need to sometimes generate this event graph to see what types of graphs, what types of copies were inserted by the runtime. And this graph is more comprehensive in the sense that it covers more, more types of operations, like acquire, release, and even phase barriers between the operations. I'm not going to talk about in detail about this, but I'll explain these later in the talk. Actually, in the next talk. And each of the tasks, as I said, has more information about the task. So it will show you which physical instances are being used for this task and the privilege on all the logical regions. And this graph will also show the implicit dependency between parent task and the child task. This is another type of graph called instance graph, which shows a similar amount of information as the event graph. But this will give you instance-centric point of view of the dependency structure. So here, you will see these ovals here. These are actual physical instances that are created during the execution. And the edge between task and physical instance means that this task is accessing this physical instance. And the relationship between instances mostly due to the copies. So if you see many of these dashed, the dotted edges between the instances, that means that the runtime inserted a lot of memory copies between the physical instances, which might be some sign for the performance tuning. Again, another type of graph. This is a partitioning graph. This graph will show you the structure of your index space and partitions, and also logical regions and logical partitions here. So I'm going to talk about debugging support from legion and region from now. So in both legion and region, we have to specify some of the index partition is whether alias or disjoint. So in C++ API, you can pass the argument here to say this index partition is disjoint. And also in region, you can pass the keyword disjoint for a partition. But there's no way to statically check without the DPL language that Sean talked about to check whether the partition is actually disjoint or not. So we add a runtime check for disjointness of partitions. So when you pass -HL:disjointness, then it will give you information about whether you violated the disjointness condition.
Does this include disjointness of the underlying data in any way, or just the actual indices themselves?
This checks whether there are two subspaces that overlap each other. So this is mostly about the structure of the data, not the data itself. Okay. And second type of check is a privilege checks. In Legion, we use a C++ API, so there's no way from the compiler to know that whether the task body is actually abiding by the requirement that it requested. So for example, here I request a read-only privilege for this logical region, but somehow here I'm doing the write operation to the logical region, which means that I'm violating the region requirement. But this kind of violation cannot be detected statically from the C++ compiler, so we add a compile time flag to insert this privilege checks and report when there is a violation here. But the same check can be done statically with the region compiler, because region has a type system that tell you whether your region application satisfies all the region privilege of the tasks. So once the region application is type checked, then there's no overhead to check the privilege violation. So for example, this is a region application, and the task check says that it's gonna read the region R, but inside the task, it tries to update the region. And this kind of violation is detected as a type error from the region compiler. So here you will get that there's an invalid privilege for the logical region. So finally, we also provide the bound checks in region. So sometimes you have to find whether you are making any access that are out of bound for a region boundary. So when you think that there's a data race between your tasks, you might want to enable these bound checks and to see whether there's any bound, out of bound accesses. And this kind of array bound check is very heavy weighted, so it's only enabled by the compile time flag. So you have to recompile your application to insert the check code.
You talk about how expensive those three things are relative to each other, just to give people a feel. I can do it too.
You can do it. Yeah.
Back up with this slide to the, what was the, go back and do slides. Yeah, let's do the disjointness one first. So disjointness checks are pretty expensive because you literally have to touch every element and check to see what's disjoint within it. You will notice that in some of the new partitioning APIs, we're actually going to give you a third option here, which is normally today we ask you to specify a Boolean, is it disjoint or not, is it aliased? There's actually going to be a third option on a lot of the new partitioning API calls that will actually ask you to tell the runtime to actually compute it. The runtime will actually compute whether or not your partitioning is disjoint or not for you. And so, and we will memorize the results of those computations, but they are a little bit more expensive. So, if you know, you should tell us, and then you can use the HL disjointness check to check it. Otherwise, it would be good to actually have the runtime compute it just to be safe. Can you go on to the next one? The privilege checks are actually not very expensive at all, because effectively I guess they're a little bit expensive because you're actually checking that on every read or write that your accessor is going to do. So they can be a little bit more expensive, just because every single memory access that you do through an accessor is going to incur a branch. And then the balance checks, are also fairly expensive because you literally have to check, multiple branches for every pointer or point that you dereference. You have to check it against one or more bounds. So, I haven't actually profiled any of this. Have you done any?
No.
But, it's not unexpected. If you start turning on privilege and balance checks, not to expect, a few X slowdown. Literally, because on every memory access, we're going to be checking to make sure you're doing the right thing. It's almost like turning on Valgrind, which I think is like a 10X hit on your application. So, don't be profiling stuff with the checks on.
I mean, that kind of thing is not too hard to statically check if you have the type of the accessor depend on the privileges passed in. But I guess the privileges passed in if the privileges would have to be passed in as a template parameter of some sort.
Right,
Have you guys looked into that?
Did you look into that, actually?
Yeah, I can answer that.
Yeah.
Yeah, I mean, as much as possible, we've tried to avoid templates in the API. You notice that the legion.h header file, has very minimal template instantiation. Only when we really absolutely needed do we try to use templates. But in fact, actually a very early version of Legion had templates to check some of this accessor stuff. And you just found that the API just gets more and more nasty the more templates you include. So you want to say something too?
Yeah, I was going to add a different reason. There are a few cases where we've taken advantage of Legion being a runtime API to actually have tasks whose behavior is dynamic. We actually look at the state of the system and decide what privileges a task needs based on, for example, is this a time step where I'm going to do a checkpoint? No, then I don't need to write out these intermediates. I can skip them. Yes, and then you run into combinatorial explosion in a few cases. So yeah, basically the templates tend to multiply in painful ways once they get near each other, and so. But yeah, the main thing is a design choice on the C++ side that the privileges are actually completely unrelated to the task declaration at the moment, and you could choose to address that. Our approach is to lift it up to the region level instead.
Okay, so from this point, I'm going to give you a kind of small exercise, how we optimize Legion applications using these tools. In particular, I'm looking at the mini arrow, which is developed by Sandia, and we are working on optimizing mini arrow in many different ways. And here's one example of how we use our tools. So in order to optimize the performance, we have to first measure the performance. So I run a big enough problem size with 2 million cells and 7 million faces. And I run it for 5 iterations on 1, 2, 4, and 8 CPUs on a single node. And here's a graph. So I got 5x speed up at 8 CPUs, which seems reasonable, not very bad. But I thought, is this the best performance we can get from the 8 CPUs? So I first profile the 8 CPU case here. And this is the entire Legion prop result. And you can see that there are a lot of instances created during the execution. There were 115 instances, 5.7 gigabytes in total. If you go back to the problem side, it's only 2 million cells and 7 faces. So this couldn't be the case that we use this many instances. And I also take a closer look at the task level here. Then you can see that there's a small gap between tasks. Even this fit to the entire timeline. So I zoomed in and found that there are some low-level copies here that somehow blocks the task being executed for this particular case. These blue copies mean that this copy is initiated by the following task here. So this copy is on the critical path. So next step we have to do is to get an event graph of this run. So as I said, the real execution is too big to fit into a single graph, so I reduce the problem size to get the dependent structures and which copies are inserted by the runtime. And here I found 48 tasks and 142 copies between instances. But if you think about the structure of this mini arrow, what mini arrow does is that it partitions the mesh into several partitions, several blocks, and each task only acts right to its own block and only make a read access from the other block. So I think this is not, it doesn't make much sense to have this many copies here. So I, again, zoomed in and found that. So here you can find that this compute limiter task is requesting field 210. But here, the compute phase flux requests a bigger instance with more fields. But somehow, the previous task is not reusing the same instance, but making a separate, smaller instance and issues a copy between the smaller one to the larger one. And if we can somehow make the task reuse the physical instance, then you can avoid this type of copies.
Sounds pretty familiar from my talk this morning.
Yeah. So same kind of intuition you can get from the instance graph. So here you will see there are physically 2 instances where the second one is a superset of the first one. but still you have to make a copy between the two. So from this information, we decide to write a new mapper for mini-arrow. The basic trick here is that we add all the necessary fields up front. Yeah.
Yes. This is back up there. I just thought I would interject here that that sometimes you actually would want the two instances. I mean, in the first case, you have a smaller set of fields, and if it were the case that because of other kind of memory problems or memory pressure you were having, that you needed to reduce the size of the data in order to do your computation locally, it might be exactly the right thing to have a separate copy without all the data in it. It just happens that in this case that it was the wrong decision. All right, so this is exactly the kind of thing where you want to provide some flexibility depending on the particular application, which way is the right way to go.
Right, as Alex mentioned that if there is a chance to optimize by making a copy to relax the word dependency between the tasks, then this kind of smaller temporary instances might make sense. But in particular case of mini-arrow, this is kind of waste of runtime resource. So we decided to create a new mapper that basically add all the necessary fields to the instance when it's first time created. But it still needs to make some copies between the instances when you run mini-arrow on multiple nodes and you access the ghost region from one node from the other. And again, the new mapper API will even allow us to map one logical region to a union of physical instances that cover the requested fields. But with the old API, this is the option we choose. So we run mini-arrow with new mapper. And you can see that there are only 4 physical instances. There's no boundary between here, but I count them. And if I zoomed in, there is a smaller gap between the tasks. And in this instant graph after tuning, you will see that all the tasks are accessing the same physical instance. This is kind of nice to see when your tuning was successful. So this tuning is translated into a better performance here. So we now get 6.5 speed up on 8 CPUs. If you take a closer look at this gap between these circles, and on 8 CPUs, there is a larger gap compared to the initial ones here. Okay, so this is the end of my talk, and happy to answer questions.
So part of writing that custom mapper is there was hardwired in there, there's 8 fields here and there's 12 fields here, and so is the new mapper interface going to have a way to make that much more robust? Because right now with the current one, if we add a new field to mini-arrow, it breaks the mapper because it doesn't know how many fields there are. Is the new mapper interface going to be more robust in that way of being able to query how many fields should be put on there? Or? So
right now, the way you can tell about the information, about the application to the mapper is that you hard code some of the information like the number of fields or what field IDs you give to the field, each of the fields. And in the new mapper API, you can actually query about the physical instances, like which field in the field space are actually contained in this physical instance, or whether you want to create a composite instances of several instances, or you want to make a new copy when it makes sense. So this kind of decision can be more be available to the application programmers and also mapper programmers.
Okay, I wanted to toss out one other answer, which is that in the new mapping language that Wanchan is working on, right, it actually has a compiler component to it, so it can actually understand the code and just tell which fields you mean anyway. So you could just put star there, and it could figure out which fields you mean.
Any other question?
I see like you guys have a lot of if you just look at the fields, for example, 202, 206, 210, are those the enumeration IDs? How to make sense of it? Can we tag them so that we can search it?
Yeah, you can attach a name to each of the field. So there's a Legion API to attach a name.
Yeah.
And also you can let runtime pick the field IDs.
As they are right now.
So those IDs there were all chosen by the application code.
Yeah.
Oh, okay. So these are already okay. So okay. That's what I was experienced before, but I'm not sure right.
I think that's a bug in Legion Spy. So
okay.
yeah, I will take a look. Yeah, could you make a GitHub issue for us?
The ACPUs is still on one node, right?
Yes.
Is the off node version working yet, or
Which off-node version are you
the
talking about?
multi-node version working yet?
Miniero? Yeah. That's the next talk.
Oh, sweet.
It's the next topic. Yeah. For your information, I'm giving the next talk, so
Yeah, he's stuck giving the next talk too. So.
yeah. Please bear with me.
Given that there is a next talk, you can sort of guess what the answer is.
That's true. Other questions?
Oh, to answer your question, if you go back to this graph, this is multi-node from Miniero. But again, it's transformed in a way that I'm going to explain in the next talk.
Thank you. So I think Legion has ambitions of being very scalable. And so I would also want the tools to be very scalable, meaning that if I notice that I'm doing fine up to 30,000 nodes, but then after that things go south, do you have any facilities for that? So then that stuff doesn't fit on one screen anymore. If you think about it in the simplest form, canonical form, do you have tools to extract data from very large-scale computations? Performance data. I'm not talking.
You mean the Legion Prof or Legion Spy?
The profiler.
So for Legion Prof, this timeline has implements some nice trick to hide much of the information when the zoom level is too high, and it will only show the smaller boxes when you zoomed in like this. Oh, sorry, it's not giving you. So you will start seeing some of the blocks when you zoom in.
I'm not talking about zooming in, but so I'll have 50,000 resources that are executing tasks.
Right.
So many timelines that won't fit on a screen. So we need to do something. That's a problem many people have looked at, and it's very hard to do anything rational. But since Legion is specifically meant for very large-scale computations, I think it would merit attention.
So I'll answer this question because I've actually used some of the Legion Prof and Legion Spy tools when we did some of our 10,000 plus node runs on Titan. Some of the visual aspects are not so scalable at the moment, but the actual data processing stuff is very efficient. We've done some optimizations to really make it so they load files. You can load 10,000 files that each have a gigabyte of data pretty quickly, and actually process and churn through that data pretty efficiently. One of the things that we learned doing S3D that we haven't really generalized yet to things like Legion Spy and Legion Prof yet, but we sort of realized is very important is we built some tools to process S3D performance data, and it looked for what we were calling anomalous behavior. Effectively, how do you recognize the interesting timeline, right? The one that's bad, or the few that are bad, as opposed to them just seeing the whole 10,000 of them and having to look at them all individually and process them as a human. How can you actually realize where the anomalous behavior is? So we had some very specific tools that did this for S3D, and they could scale out to 10,000 plus nodes. We haven't actually bothered to generalize that yet to Legion Spy and Legion Prof, but I think we know the tricks now how to do that. And so, as more people start to scale up, I think we can sort of, we want some more use cases, obviously, to drive the anomaly detection behavior, right? How do you define what an anomalous behavior is, and do you want to say something? Excuse me. And so how do you recognize what anomalous behavior is, and how do you see that in multiple different kinds of applications, and then have something like Legion Prof or Legion Spy say, oh, you're getting anomalous behavior right here, and show you a very specific picture of what's actually going wrong.
So that would come out first when you compare, say, two computations, one with a certain set of nodes and then doubling, for example, and you see that some tasks disproportionately get slower than others. So you want to compare these different runs. I think there would be a lot of value to that, particularly at a very large scale.
Okay, so the other thing I wanted to add is all this Legion Prof and Legion Spy stuff, well, specifically the Legion Prof stuff, is actually the profiling. This is a user of there's a Legion underlying profiling framework that works with the mapping interface that feeds back profiling information to the mapper. And the data that Legion Prof is using is data that's output by a very, very simple set of code there that basically just dutifully writes down all the answers into a text file for this post-processing step to visualize for you. But the interface is designed to be very extensible, and again, it's in the mapping interface, which means that an application can either write their own or use some third-party library code to do more online analysis, more online filtering, anomaly detection type stuff, and capturing just the parts that are interesting, for example, or doing the statistical analysis possibly that then lets you find the anomalies later. So just writing all the answers down to a text file is one simple thing you can do with the profiling interface, but we're expecting a lot more, both in terms of detecting performance bugs after the fact, but also in terms of doing in situ online tuning of your application.